Good morning and welcome to this next lecture on vibrations of plates and shells. So last time we derived the equation for the Euler-Bernoulli beam in the manner that it is done in the book to give you a feel through a simple example. Okay. So now we did say that a beta definition has to be brought in. So let us see first the epsilon 1 3 we had is A1 1 plus alpha 3 by R1 del alpha 3 U1 by A1 1 plus alpha 3 by R1 plus 1 by A1 1 plus alpha 3 by R1 del U3 by del alpha 1. This is what we said. Okay. Now we brought in the beta. So U1 became U1, which is a function of alpha 1, alpha 2, alpha 3, became small u1 function of alpha 1, alpha 2 plus alpha 3 plus alpha 3 times beta 1, alpha 1, alpha 2. Okay. So we will put it in there. So my epsilon 1 3 is A1 1 plus alpha 3 over R1 del alpha 3 small u1 plus alpha 3 beta 1 by A1 1 plus alpha 3 by R1 plus 1 by A1 1 plus alpha 3 by R1 del U3 by del alpha 1. Okay. Now this we are going to set as 0. So this is 0. Okay, 0. Once we have 0, I can multiply by A1 1 plus alpha 3 by R1 both sides. Okay. So I get 0 is equal to A1 square 1 plus alpha 3 by R1 whole squared del alpha 3 U1 plus alpha 3 beta 1 by A1 1 plus alpha 3 by R1 plus del U3 by del alpha 1. Okay. So what do I have now? What I have is del U3 by del alpha 1 is equal to a minus A1 square 1 plus alpha 3 by R1 whole squared. Okay. Then del alpha 3 of the numerator, which gives me beta 1 into denominator A1 1 plus alpha 3 by R1 minus derivative of the denominator, which is A1 by R1 into the numerator, which is U1 plus alpha 3 beta 1 and square of the denominator. Square of the denominator. So this goes with that and I get minus beta 1 A1 plus beta 1 A1 alpha 3 by R1 minus A1 by R1 U1 minus A1 by R1 alpha 3 beta 1. So this goes away. Okay. So then for beta 1 I have, for beta 1 I have U1 by R1 minus 1 by A1 del U3 by del alpha 1. Similarly, beta 2 will be U2 by R2, this is small u1, small u2, minus 1 by A2 del U3 by del alpha 2. Okay. Now, a further simplification we are going to do under the assumption that we are going to work with thin shells, okay, is that wherever we have alpha 3 by R1 or alpha 3 by R2, we will consider this to be much smaller than 1. Okay. So that now we will get epsilon 1 1 is equal to 1 by A1 del by del alpha 1, we bring in beta u1 plus alpha 3 beta 1 plus 1 by A1 A2 del A1 by del alpha 2 u2 plus alpha 3 beta 2 plus u3 by R1. Similarly, epsilon 2 2 is 1 by A2 del by del alpha 2 u2 plus alpha 3 beta 2 plus 1 by A1 A2 del A2 by del alpha 1, okay, u1 plus alpha 3 beta 1 plus u3 by R2. Epsilon 3 3 is 0, so is epsilon 1 3, so is epsilon 2 3. Okay. And epsilon 1 2 is A2 by A1 del alpha 1 u2 plus alpha 3 beta 2 by A2 plus A1 by A2 del alpha 2 u1 plus alpha 3 beta 1 by A1. Okay. So this page will be useful somewhere, I will need it, so let me mark it that way. Let me mark it with red here. Now you can see here, that in here there are some terms which have no alpha 3 in them, because this is just a function of alpha 1 alpha 2, this is a function of alpha 1 alpha 2. So only this term has alpha 3 in it, only this term has alpha 3 in it. Similarly, only this term has alpha 3 in it, this term has alpha 3 in it, this term and this term. Okay. So we can write these, so we can write epsilon 1 1 as an epsilon 1 1 0 of the mid surface plus alpha 3 times the remaining term. Similarly, for alpha epsilon 2 2 is equal to epsilon 2 2 0 plus alpha 3 k 2 2, okay, and epsilon 1 2 is epsilon 1 2 0 plus alpha 3 k 1 2, okay. So these are all nice to have them in one place. So epsilon 1 1 0 is 1 by A1 del U1 by del alpha 1 plus U2 by A1 A2 del A1 by del alpha 2 plus U3 by R1 epsilon 2 to 0 is equal to 1 by A2 del U2 by del alpha 2 plus U1 by A1 A2 del A2 by del alpha 1 plus U3 by R2, then epsilon 1 2 0 is equal to A2 by A1 del alpha 1 U2 by A2 plus A1 by A2 del alpha 2 U1 by A1, okay. Then the case K11 is given by 1 by A1 del beta 1 by del alpha 1 plus beta 2 by A1 A2 del A1 by del alpha 2, then K22 is equal to 1 by A2 del beta 2 by del alpha 2 plus beta 1 by A1 A2 del A2 by del alpha 1, and K12 is equal to A2 by A1 del by del alpha 1 beta 2 by A2 plus A1 by A2 del by del alpha 2 beta 1 by A1. This is also a page I would like to note, okay. Now if we look at the sigma, okay, we are now heading towards force and moment resultants. Which arise as soon as we integrate with respect to z or alpha 3, okay. So we have to, we will formulate them ahead, okay. So we will formulate them right away. So we have sigma 1 1, let us see, sigma 1 1 given by E by 1 minus mu square. I am writing them all in one page, so I can come back to retrieve. Sigma 2 2 is equal to E by 1 minus mu square epsilon 2 2 plus mu epsilon 1 1, and sigma 1 2 is epsilon 1 2 into G. Let us just take sigma 1 1. Okay, the sigma 1 1 now written in terms of mid-plane strains and bending strains, E by 1 minus mu square. Okay, we will call these the bending strains. We will call these the neutral mid surface strains. Okay, so that sigma 1 1 now is equal to epsilon 1 1 0 plus mu epsilon 2 2 0 plus alpha 3 k 1 1 plus mu k 2 2. Okay. So, in the entire expression alpha 3 comes only here. Okay. So, now if we look at how sigma 1 1 comes up, okay, so we have this is the alpha 1, or let me do this. This is what happened. This is alpha 1, this is alpha 2, this is alpha 3, and let us say I have a thickness over here. Then sigma 1 1 will be coming out like this, sigma 1 1, and let us say this is the mid surface, and let us say hypothetically this is how it looks like. Okay, and this is R2, so this is R2, this here is R2. Okay, so this element length is A2 d alpha 2. You should know that now. D alpha 2 is the coordinate change, A2 d alpha 2 makes it a length. So, that length divided by R2, okay, gives me an angle. And now if I want a location away from the mid surface, okay, then that length is R2 plus alpha 3. Okay. So, therefore, a length element at a general location is A2 d alpha 2 1 plus alpha 3 by R2. Okay. So, the area element now will be this length into d alpha 3. So, that is d alpha, that is an area element. Okay. So, that is an area element, this. So, this is d alpha 3. Okay. So, now if I multiply by the normal stress, then that is a force over this elemental area. Okay. So, if I now integrate from alpha 3 is equal to minus h by 2 to alpha 3 is equal to h by 2 of sigma 1 1 a 2 1 plus alpha 3 by r 2 d alpha 2 d alpha 3. Okay. So, now what happens here? What happens is that we said we will ignore all alpha 3 by R1 and alpha 3 by R2 type terms. Okay. So, we drop that term. So, what happens is we get the okay, let us say first the N11 axial force resultant. Axial force resultant is first given by minus h by 2 to h by 2 sigma 11 1 plus alpha 3 by R2 d alpha 3. Okay. You can see stress multiplied by one area element. So, it is not a full force. Okay. What is left is A2 d alpha 2 is left. Okay. So, this would have made it the full force, let us say 1 1. So, this divided by A2 d alpha 2, this is the force resultant, this is N11. Okay. Further we drop this alpha 3 by R2, that means N11 is equal to integral minus h by 2 to h by 2 sigma 11 d alpha 3. Okay. So, this he wants to write as a k, okay, times epsilon 110 plus mu epsilon 220. Okay. The reason is this: sigma 11 carries, if you remember, terms independent of alpha 3 plus alpha 3 times some term. Okay. So, if we now integrate this from minus h by 2 to h by 2, the alpha 3 becomes alpha 3 square by 2, which over the limits minus h by 2 to h by 2 will go to 0. So, the k terms, k do not feature. Okay. So, this, what is this k? This k is the membrane stiffness, which is E h by 1 minus mu square epsilon 110 plus mu epsilon 220. That is your normal axial force resultant, force per unit length. Okay. Similarly, N22 becomes E h by 1 minus mu squared epsilon 220 plus mu epsilon 110. Okay. There is E over 1 minus mu square in front, this term is 0, this is a constant, alpha d alpha 3 becomes h over limits minus h by 2 the h plus h by 2, that is why this h comes in here. Okay. And N12 and N21 are equal with this denoted as k, this thing denoted as this constant k into 1 minus mu by 2 epsilon 120. Okay. Now for the moment resultants, what happens for the moment resultants? I have sigma 1 multiplied by a length at a height alpha 3 multiplied by the d alpha 3. Okay. So that gives the full force. Okay. However, we multiply by the height alpha 3, that makes it a moment. We multiply by one more alpha 3. Okay. So this is now a full moment. So let me call it star, it is a full moment unit. Stress into area, full force into length, full moment. Okay. So here we will again drop alpha 3 by R2, okay, and A2 d alpha 2 comes in the denominator. So M11 star A2 d alpha 2. So the resultant is M11, the moment resultant. Okay. So that is M11 is equal to integral minus h by 2 to h by 2 sigma 11 alpha 3 d alpha 3. Okay. That is equal to d k11 plus mu k22, where this thing d is the bending stiffness. You must have seen this somewhere. Okay. So similarly, M22 is d times the symmetric term, and M12 is equal to M21 is equal to d times 1 minus mu over 2 k12. Okay. So let me do some marking in case I come back here. Okay. And lastly the transverse shear force resultants Q13 is integral minus h by 2 to h by 2 sigma 13 d alpha 3, and Q23 given by integral minus h by 2 to h by 2 sigma 23 d alpha 3. So we have run out of time, so I will stop the lecture here. We will continue from this point next class.